Okay, so this is the next question that we have on the menu today, and it's asking us 2-point charges. One is 3 microcoulombs, ignore the A accent circumflex, and the other one is 6.1 microcoulombs, and they are separated by 1.4 meters. We are looking for the electric potential midway between them. Okay, so let's actually draw a diagram to represent what this situation is. So let's draw the first one. Let's make this Q1. We have 3 positive 3.2 microcoulombs and we're looking for the point halfway between them. So let's just call this R and R. Since we're halfway between, they have to be the same. And here we have Q2 negative 6.1 microcoulombs. Okay, so let's call this point of interest point A. So we're looking for the electric potential at point A. So essentially, the procedure that we want to follow here is we want to find the electric potential as caused by each one of those charges individually and then add them up. So find E potential of individual sources and add them up. Okay, that should be the way to go. The equation that we want to use for finding the electric potential we often represent it with the variable V, representing voltage, but we want to say electric potential instead of voltage because we normally say voltage more in the respect of electric circuits and electric potential in like more static electric situations like this, but we often use the letter V. Here we use the letter, they use E to represent the electric field, but I actually have an easier procedure for how to solve this. This is just K Q over R. Yeah, so KQ over R. So we know that R is going to be the same for both of them. So our V at point A, let's call it VA, is going to be equal to the V from Q1 plus the electric potential from Q2. And subbing them out, we have we have Q1 for that one plus K Q1 over R for the second one. Okay, Q2, not Q1. Okay, cool. So let's sub in our numbers, and actually, before we sub in our numbers, let's do some factorization to make this calculation a little bit easier for us. So our VA, we see how K over R is common to both of them, so we can factor that out, K over R. And this shall be, what's left is Q1 plus Q2. Okay, now R is going to be half the distance between them. And because we know the full distance between them is 1.4 meters, we know that this has to be 0.7 meters. 0.7 meters. Okay, so that's our R value. Our K value is Coulomb's constant. So let's actually just start subbing in our numbers. So we have 9 times 10 to the 9 for our Coulomb's constant. R is 0.7 meters. Q1 is positive 3.2. 3.2 times 10 to the negative 6 coulombs plus, and our second charge is negative. Okay, keep in mind it's negative, and we have to have that negative associated, or that negative needs to be here. So negative 6.10 times 10 to the negative 6 coulombs And this will be our electric potential at point A, halfway between them. Okay, so let's do this quick math. So we got, in the middle, we have 2.9 times 10 to the 6, 10 to the negative 6, 2.9 times 10 to the power negative 6, multiplied by 9, multiplied by 10 to the power of 9, and all divided by 0.7. So my calculation for electric potential here has to be 3. It's actually going to be negative, right? Because since this overpowers that, it has to be negative inside the bracket, and the negative, there's no negative out here to counteract that. So it's going to be negative 37285 volts. And to adjust for significant figures, we have 3 significant figures. So we could say VA is equal to negative 3.72 times 10 to the 4 volts. And this would be our electric potential here. Cool. So that would be my final calculation. The issue here is that these are not, that should be negative. Right? The original charge here was negative, and that was not included here, so this answer is unfortunately inaccurate. So this would be a better solution is negative 37,000 volts, or 37.2 kilovolts. You can write that as well. Negative 37.2 k volts. Okay, cool. So yeah, that would conclude this question. I just got to mark that the sign error. On the 6.1 microcoulomb charge, which makes the final calculation wrong. Oh man. Seems that time flies when we have fun, as the old saying goes, and we've got to our last question. So those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please subscribe and hit the notification bell below. If you really enjoyed this video, please leave a like and a comment and share it with your friends. This has been Millen from OneClass. I hope to see you again soon. Today has been a fun time with the physics. The physics will never do you wrong. I have a great time. I hope you had a great time too. Have an amazing day or evening, whatever time you're enjoying this, and take care. Physics is good time.